And yes, the recording is now working. Excellent. Before we start, do you have any questions? Can you see my screen?
Yes, sir.
Okay, class. Well, I can see that today not even half of you are here, but that's okay. So, today, class, we have a lot of things to talk about. We will be talking about a lot of fundamental concepts. We will be talking about the fundamental concepts of system programming, and especially how system calls work. We will talk about superficially at least, we will talk about processes, especially their memory layout, the command line arguments, environmental variable lists. This is light stuff, just to get us started. And towards the end, we will be talking about memory allocation and how it works when we deal with the heap and when we deal with the stack. Now, the fundamental concept in this course is a system call. What is a system call? What is it used for? Well, it is used whenever and every time you want to interact with the system. And by system, I mean the computer. I mean the operating system. Now, what can you do with these system calls? They represent a controlled entry point into the kernel, and they enable us to request from the kernel to carry out an operation on our behalf. Bizim adımıza bir iş yapması için ricada bulunmamızı sağlıyorlar. We can use these system calls to create new processes, to perform input-output, read, write to and from devices, create pipes, carry out inter-process communication. You can name it. Now, before we look at the list of system calls, it is very important to take into account that since system calls manipulate low-level, since they manipulate low-level concepts, low-level components, since they enable us to interact with the system, that means they have to be executed in kernel mode, which means we need to have access to the entire set of instructions available by the CPU. Not just the limited set, not just the trial version, but the full packet. We need to be able to access any memory location while executing a system call. That is why all the system calls, they are executed in kernel mode. It is at that mode that the CPU can access the protected kernel memory. Now, there isn't an infinity of system calls. It's a finite number. And since they are so privileged functions, the kernel is very, very careful what it is executing. And it has a lot of protection mechanisms so that that system is not compromised. Now, before we take a look into the details, let's take a look at the list of system calls. You can find it very easily online. Can you see the list?
Yes.
Yes, we can.
Yes, you can see the list. Now here we have the list of the system calls of the most frequently encountered system calls across all the different kinds of kernels for the POSIX systems, and especially in the case of Linux. And you can see their names right at each of these columns, and it goes all the way to 190. Now, as you will see, each of them also has a number in front of them. Here, for instance, especially, we have syswrite, which is associated with the number 4. And above it, of course, we have all the signatures of these system calls and where exactly the source code is located for them. So the list is quite long. We have system calls for exiting processes, for forking processes, for reading, writing from devices, opening, closing files, waiting for process IDs, linking files, deleting files, creating new processes, changing directories, requesting the time, changing the permissions of files, and so on and so on and so on. So we have a rich spectrum, a rich variety of functions of system calls specifically available to us in order to interact with the kernel for anything that can come to your mind. So these are the functions that we are supposed to use in order to interact with the system. This is what we are supposed to use in order to carry out system programming. Now, in kernel mode, so in the mode that these system calls are executed, of course, there is a complete freedom. So whatever the instruction, it will be executed by the CPU. It has complete access to the entire instruction set, complete access to all of the hardware, nothing is prohibited, and of course it can access any memory address, any memory address. So if there is a crash, if there is a programming error, if there is an algorithmic error inside a system call, there is no way of returning from it. If it crashes, the entire system crashes. While, of course, we are in user mode, of course, we are actually playing in a sandbox, and it doesn't matter what you do. It doesn't matter how hard you try to crash the system. At worst case scenario, you will only crash the process. So in user mode, that is the protected mode, we only have access to the non-privileged instructions of the CPU. We can only access the memory locations that the kernel allows us to access. So in user mode, even if you crash in your program, you only crash the process. That's why the system can reliably stay online. That is why, besides, if you look at the records of the systems that have been online for the longest time, you will see that they are not Windows systems. You will see that they are POSIX compatible systems that have been online for multiple decades. Exactly which system is that? I will let you alone to check for those records. Now here we have a general outline of how a system call works. Now from a programming point of view, it looks very, very similar to making a C function call. Now there are 4 blocks here. We start from the top left and we advance to the bottom left. So at the top left, we have the application program. So basically, we have the code that we have written. And here we have a system call, for example, execve. We will see in a few weeks what exactly it is used for. It could be any system call. So it has a certain number of parameters. So what do? We just simply call this function. I mean, from our point of view, a system call or a function, they have no difference from the point of view of developers. So we call that function. And what happens then? Now, this function, where is it located? Well, basically what we are calling is simply just a wrapper function available in glibc, so available in the standard C library. And inside it, this wrapper function, what it has is of course, a kernel trap, so a very special instruction, the hexadecimal 80 or 128 in decimal, which enables us to switch to kernel mode. And once we switch to kernel mode, we will see later on that these parameters are switched to the kernel stack. We will talk about that in the upcoming slide. So this is the wrapper function at the top right, which enables us to switch to kernel mode. And once we are in the kernel mode at bottom right, then there the kernel takes those parameters that have been given to it by the wrapper function. It determines which system call we want to execute. It makes the necessary controls to see whether we are actually, calling a valid system call. And if everything is all right, then the kernel mode eventually reaches the bottom left and actually executes the system call. Whatever it returns, it is returned to the trap handler, to the kernel. The kernel switches from kernel mode to user mode, returns it to the wrapper function, and the wrapper function returns it to the application program. And as you can see, the bottom line is that this is not cheap from a computational point of view. Executing a system call is an expensive step, computationally speaking. You call the wrapper function switches to kernel mode. The kernel mode will make controls of all the parameters. Is everything all right? Are you calling the correct system call? Are the corresponding parameters correct, and so on and so on. Then it will actually execute the system call. Then it will get the return value to the trap handler, from trap handler to the wrapper function, from wrapper function to the application. Those are a lot of steps just for one function call. So bottom line is, we need to be careful how many system calls we make. So you need to use them in moderation, tasarruf ederek. So now let's take a closer look at these 4 steps. Step 1, the application program makes a system call by simply invoking the wrapper function in the standard C library. Now, at this point, a system call or a function has no difference from our perspective. Now, inside the wrapper function, So inside the standard C library, what is going on? Now the wrapper function must give the parameters and whatever system call we have invoked, all that information to the kernel. And of course, it has to switch to kernel mode. So it must definitely call 080 hexadecimal to switch to kernel mode. But besides that, it must also give all of those parameters. How? The kernel is not expecting them in the stack. The kernel expects all of those parameters in specific registers. And it is the responsibility of the wrapper function to place all those parameters in the corresponding registers. Here, for example, we give an example. Well, in this example, we can see how we are calling the write system call, which we can use it in order to input information into devices. So whenever you call printf, whenever you call any printf, basically fprintf, sprintf, or simple printf, write will be invoked at the lower level. We will talk about write in detail in the upcoming weeks. Here, for example, we see that it has 3 parameters. So file handle, where are we writing to which device? In this case, we are writing to std out, which is represented by the file descriptor 1. The second argument is what are we writing? So it is simply a pointer to the message, to the string that we want to write. And the third argument is simply the length of the message. Okay, so they have been placed to the registers extended BX, CX, and DX, whereas in AX, we have the number of the system call, which as you saw earlier in the list of system calls, in the case of write, it was number 4. So all of these parameters plus the number of the system call are placed in the registers, and then the wrapper function simply tells the kernel, we are ready for a system call by invoking 080 and switching to kernel mode. Now, once we switch to kernel mode, now it is the job of the kernel. Now it is the kernel that is executing. And what does it do? The kernel, very simply, it goes to the registers. It knows that all the parameters will be at the registers. And specifically in AX, it will find the number of the system call. It gets them. From there, it reads them. And now it can put them to the kernel stack. So from the registers back to main memory, but not to just any place in main memory, to the kernel stack. Now it is simply a function call. We are going to use the kernel stack. Now, the wrapper function executes the trap machine instruction, which causes the processor to switch from user mode to kernel mode and execute code pointed to by location 080 of the system's trap vector. So once we reach now the kernel mode, the kernel has read all of these register values. It has transferred them now to the kernel stack. And once it transfers them, now it checks if everything is all right. So it checks whether we have given it a valid system call number. Maybe we have given it 1 million, which is invalid. 4, that's a valid number. It checks whether this number corresponds to an actual system call. It executes the appropriate system call service routine, which of course it will find it by using the number that we have given it for the right system call. Once it is done, it will restore the register values from the kernel stack, and of course it will place the return value on that stack. And then backwards, we are returning to the wrapper function, and the wrapper function, of course, once we're there, we have returned from kernel mode to user mode, and eventually the wrapper function will return that value to the application program. Now, what happens when there is an error? Now, we will talk about errors in detail, but for now, let's say that there is a global variable accessible by all programs, even those that we write, by simply including a global variable available externally, errno, and we can check the value of this variable to figure out what kind of an error has happened. Now, whether an error has taken place or not, we will figure it out by checking the return value of the system call. But in order to determine what kind of an error has taken place, we will examine the value of this global variable. Who is setting the value of this global variable? The kernel. The kernel is setting it, depending on the error that has taken place. Any questions so far? Okay, feel free to ask whenever you have a question. Library functions. We talked about system calls. Now we are talking about library functions. What is the difference? Now, the system calls are functions. They are all functions, of course, but what makes system calls different from other functions is that they are executed in kernel mode, number one. Two, you cannot access them directly. You cannot invoke them directly. You ask through a wrapper function the kernel to execute them on our behalf. Library functions, on the other hand, they are executed, the library functions are way more in number. They are way more numerous in number with respect to system calls. Here, for instance, you can see all the C library functions, available in a standard GNU system. And as you can see, they are way more numerous with respect to system calls, way more than 190 or 180. For instance, let's see if our old friend printf is here. Well, of course, printf is here. fw printf, is printf, s printf, normal printf, and so on and so on. So it is a much longer list than the system calls. And what about these library functions? Now, the purposes of these functions is, of course, very diverse. Opening a file, converting a time to a human readable format, comparing strings, and so on. You have been using them for the past 3 or more years when you were opening files, when you were reading from the keyboard, when you were writing to the screen, and so on and so on. Now, some library functions, some of them, such as fopen, they are simply just a friendlier version, a more user-friendly version of lower level system calls, such as fopen, which is basically just a wrapper for the open system call. Why? Well, because it is easier to use it. For instance, in the open system call, we have 3 parameters, but fopen only receives 2 parameters. And instead of returning an integer file descriptor, a low-level file descriptor, it returns a pointer to a file structure, which has more a higher level of functionality. We can do more things with a file pointer than with a file descriptor. Now, this doesn't mean that every library function contains a system call inside it. Many library functions, on the other hand, they do not use any system calls, such as the ones that, for example, that compare to character strings. They are there only in order to help us achieve our goals faster. So library functions are available in the standard C library. Some of them contain system calls, some of them don't. In most cases, they are there in order to simplify the interface of system calls. Now, where is the standard C library? You will find it as glibc, as GNU C library in your Linux systems. If you look for glibc, that's where the standard C library is located. Now, let's talk about error handling a bit more in detail. In a portable POSIX system, how do we handle errors? Or generally speaking, philosophically, how should a developer handle errors? Now, a question to you. What are the options that we have when an error happens? What are the 4 options for dealing with an error? What can you do when you confront an error? Tell me.
Ignore the error.
Ignore the error. That's my favorite option. Yes, number 1. Number 2?
Stop whatever you do and exit the program.
Absolutely. You can exit the program. You can just panic. These are the 2 opposites. Either you ignore it and you say, everything is all right, don't worry, there is no error. Or number 2, you can say, oh my God, I am panicking, the system is going down, shut down everything. That's true. Number 3, what else can you do?
Maybe log the error and
yes, let somebody know.
Else.
Let somebody know. Yes, print it on screen, log it down, send an SMS, send an email, send a WhatsApp message, inform the administrator, inform somebody. That's true. And number 4, the one that we are supposed to be doing.
Try to understand it.
Yes, and after you understand it, fix it.
Solve it.
For instance, the system is asking you for your name, and you enter from your keyboard 1453. So the system, what does it do? It asks you for your name politely again. That's a way of handling an error. So those are the 4 options that we have. Ignoring it, fixing it, letting somebody know, and what was the fourth one? You said ignoring it?
Shut down.
Yes, and
Understanding
shut
the
down.
problem.
Yes, quitting. Absolutely, quitting. Okay, so what about POSIX systems now? What about portable operating systems? What are the rules in the POSIX world? In the POSIX world, the rule is if there is an error on a system call, it will return -1. Negative numbers, negative return values are dedicated to errors. So if you want to have a portable program, if you write your own functions and you expect them to be portable, negative return values are allocated, are dedicated to errors, and especially -1. 0 is dedicated to normal execution. If everything went all right, it will return 0. If there was an error, it will return a negative value, and very probably it will return -1. If an error didn't take place, but something weird, something extraordinary has happened, it will return a positive value greater than 0. Hocam, how am I supposed to know which system call returns which value? The man command is your friend. Whatever you want to know about a system call, what do? You open up the terminal, even if you don't have internet, and you type man space the name of the system call. For example, write. Now, if it gives you something other than a system call, that means you are looking at the wrong man page. So we look at the second page. And here we have it. The page, documentation for the write system call. Description, what does it do? What is it good for? What does it return in case of error or in case of normal execution? What are the types of errors that you can encounter with the system call? To which version of POSIX does it conform? Additional notes, some bugs that are known, and what are the also related system calls with it. There is a man page for every system call available on every POSIX and GNU Linux compatible system. The man page is your friend. Whatever questions you have about them, it will very probably be included in the man page. Some of them even have examples, code examples on how to use them. So man command, your friend, use it, benefit from it. While we are doing system programming, while we are writing programs that actually manipulate system calls, how are we supposed to approach them? The idea is very simple. Never, ever assume that a system call cannot fail. Even something as simple as malloc. Malloc can fail. Can you give me a reason for malloc to fail?
Not enough space.
Not enough space. Is malloc a system call? No, it isn't. It is a library function, by the way. We will get to that. Now, what is the principle? The principle is never assume that a system call will not fail. So what do we do based on that principle? Always check whether a system call has succeeded or not. Here, for instance, this person is trying to open a file. He is expecting a file descriptor. So what does he do? He checks the value that has been returned by the system call. If it is -1, that means it has failed, so it is trying to handle it. It does some other stuff over there. Then it is trying to close the file. It is checking again whether it has failed. At this point, you might ask, yeah, hocam, we are closing a file. How can it fail? It can fail. Hocam, what if I don't do it in this way? What will happen? If you do not check the return values of your system calls, very probably someday they will fail, and they fail quite frequently. And because you haven't checked the return value of the system call, you will lose very probably hours trying to debug that problem. So I'm just trying to save you time. So what do? When a system call fails, of course, it will set the global integer variable erno to a positive value that can help you to identify the error. So that means if you want to use erno in order to understand which error has taken place, you must include the header file erno.h, which will also include the declaration of erno. and of course all the constants related to the error numbers. Here, for instance, we have an example. The user is trying to read from a file represented by FD, the file descriptor. He is trying to read num bytes into the buffer buf. So he checks the return value. If it is -1, that means an error has taken place. Then the user is checking the value of erno. If it is equal to the constant inter, that means an error has taken place because the read system call was interrupted by a signal. Now, what do you do after you determine the error? That is up to you. You can ignore it, you can shut down, you can try to fix it, you can let somebody know. That is up to you. If you can fix it, try to fix it. So after each system call, we are supposed to have such a block, basically, where we study the type of the error and act accordingly. This is the general rule. This is the general guideline. Hocam, this appears to be a bit complicated. Isn't there a simpler way of handling these errors? Yes, there is a simpler way. The POSIX system also provides us with two useful library functions. These are not system calls, they are library functions. Perror and str error. Perror is very simple. It is used in order to notify, to let somebody know that an error has taken place in a more user-friendly way. Basically, you just call perror and you give it a message, a string. What does perror do? It prints to standard error, not to standard output, the string that you have given it, followed by a string representation corresponding the current value of erno. Hocam bu ne demek ya? Example. Here we are trying to open a file with fopen. Now fopen is a library function that will call a system call inside it, the open system call. We are checking if it has failed. Now if the system call has failed inside it, fopen will also fail and it will return null. So if it returns null, we are simply printing perror error inside it. And what do we see on screen? Error, 2 dots, no such file or directory. Now this message came from the kernel because the kernel saw that erno has been set to this type of an error. So this is the message corresponding to that error. So it is just a simpler way of accessing the corresponding string describing the error. There is also str error available as a library function, which simply does, well, it has a very simple purpose. You give it the number of the error, so the value of erno, and it returns the string corresponding to it. So if you give it, I don't know, 16, it will return no such file or directory. So where is the list of erno? IBM documentation for VAC. Okay, we accept the cookies. So here we have the values, for instance. Domain error, range error, permission denied, file exists, no such device, no such socket, too many open sockets, file name too long. So these are the numbers corresponding to them. And here you can see the constants. Here, for instance, you can see inter, interrupted function call, 120. So erno, whenever the error takes place, is set, the variable erno is set to one of these numbers, to one of these positive integer values to represent the type of the error. And you can use str error, the function str error, to convert that number to the corresponding string. That is the way with POSIX for the last 40, 50, 60 years now. What about library functions? Well, with library functions, there is no guarantee that they are going to use erno. Erno is reserved for system calls. Some library functions use it, some of them don't use it. So be careful. Do not attempt to use erno, perror, or str error with library functions. These things are reserved for system calls. İdo hocam, how am I supposed to know which one is a library function, which one is a system call? Check the lists. Check the lists of library functions and system calls. Check the manual pages in order to be certain what you're executing. If you're executing a library function, you will not get help from erno. It is up to you to check the value that is returned. It is up to you to check the documentation of that library function to figure out what has gone wrong. If you are invoking a system call, well, in that case, you can rely on erno and perror and str error in order to figure out what has gone wrong. Any questions about errors before we switch to processes? Okay, class. Now, let's talk about processes. We will talk about processes a lot this semester. Today, it is only a superficial. We will cover it only superficially, just the organization. There will be very few system calls that we will mention. And next week and the week after that, we will talk about system processes very intensively. Now, what is a process? A process is an executing program. What is a program? A program is simply an executable file that you have written and that resides on your hard disk. When you execute that program, that exe file, that binary file on your hard disk, and it becomes an entity in memory, in actual main memory, then we are talking about a process. So this is a terminology in order to make the distinction between the two. A process is an executing, is a running program. A program is just a file. Now this file, this executable file, of course, contains all the information that is necessary in order to execute a binary file. For instance, let's go to /bin, where we have all the executable binary files of the system. We have the ls command, cd command, all the commands basically that are available to us. Okay, so all of these are binary executable files. I can see the executable permissions right next to them. Now, what do these files contain? Now, at the minimum, they must contain one, the binary format identification. So basically a meta information, so information about information that will let us know how the file is organized. I can use the file command, for instance, with ls. If I use the file command with ls, the first thing that it tells me is that this is a ELF 64-bit file. Now the ELF is an international format. It's a portable format of how executable files are organized. It is not the only format, but it is the most frequently encountered executable file format. So we can see all the information related to it, an LSB shared object, the architecture, version, it is dynamically linked, etc., etc. So the binary format identification, of course, the file will contain the actual machine language instructions, naturally, the instructions to execute. It will, of course, contain an address telling us at which instruction this program starts. It will, of course, contain the data. So the initialized data, arrays, strings, etc., etc., will be inside that executable file. It will, of course, have a table of symbols. So which function name corresponds to which address and so on, which variable name corresponds to what. It will have, of course, shared library and dynamic linking information. So for instance, it will contain that, hey guys, this program is using the printf function, which is located here or here. So printf function with this signature, which is admitting these parameters and returns this. And it is the job of the kernel to figure out where that printf function is located in the system in order to run it when the time arrives. Long story short, one program may be used to construct many processes, or alternatively, many processes may be running the same program. So you can have this one ls executable, but of course you can have multiple processes executing that program. Now, a process, of course, is an abstract entity. It is defined, of course, by the kernel. And what the kernel does is when you execute the program, it allocates resources to it. It needs to make a lot of preparation in order to convert the program to an actual process taking place in that system. Now, what kind of preparation does it require? A lot of things. Now, first of all, from the kernel's point of view, a process consists of user space memory containing program code and variables used by that code, plus a range of kernel data structures. So it needs to allocate memory to it in user space memory, put all the variables, all the code to execute in that memory space, and additionally, it needs to create a lot of data structures on its own. The program didn't ask it to create those data structures. It is the kernel's responsibility to create those data structures. What kind of data structures? Well, it will need one data structure to keep track of which pages of memory the process is using. It will need another table to keep track of which files this process has opened. It will need another file to keep track of which signals it is supposed to deliver to this process. Which of them are supposed to be handled by signal handlers. It needs to keep track of how many files are open, how much memory it is using, where is the current working directory, and a long list of other information. Long story short, it needs to make a lot of preparation to create a new process. What we need to remember, creating a new process is an expensive step. It's an expensive step computationally, resource-wise, it's expensive. So what are we supposed to do? Aren't we supposed to create new processes? Of course we have to create new processes. But this means if you can do something with one process, do not redundantly, unnecessarily create multiple processes for it. Create multiple processes only if you have to. It is an expensive step. Let's say that we have a process. So what do we know about it? Now, every process, since they can be running the same program, we cannot identify them using their file names because one program can be represented by multiple processes. So what do? Every process has a unique numerical, positive, non-zero ID. How do we access that ID? Simply by calling getPID. Sorry. This is a system call available in the Unix standard header. It has no parameters, and it returns the numerical as a short integer. It returns the identifier of a process. Whichever process executes getPID, getPID returns his process. And you will see here that it is always successful. So this means this system call cannot fail. As opposed to what I told you in the beginning, there is no way for this system call to fail. So this is an exception to the rule. GetPID and getParentPID are two exceptions of system calls that cannot fail. They are always successful. Now, each process, of course, has a parent. Hocam nasıl olur ya? The parent of a process is the process that created it. İyi hocam, who created the first process? The first process is created automatically when the system boots. Hocam, where can I see that? PS command. The PS command gives us the processes that are executing in the system right now. And here I can see the process ID of those processes. And I can see that number 1 is init. Number 1 is always init. It is the process that is created at boot time, and it is the process that creates all the other processes. So normally, the child of init will have 2 as a process ID. Maybe that child will create other processes, and so on and so on. And this leads to a hierarchy. Bir hiyerarşi, bir sıra düzeni oluşturuyor. At the top you have init, at the root, so it is basically a tree. The parents have children, the children have children, grandchildren, and so on and so on. And all of them have a unique process ID.
Is it possible to kill the first process?
It is not possible to kill the first process because the first process belongs to the root. Here, at the user column, you can see to which user the process belongs. And we, as users, not root users, we cannot kill processes that belong to other users. And especially, we cannot kill the processes that belong to root. Now, if you have root privileges, so with sudo, and you try to kill init, then yes, then you can do it. And then the system will go crazy. It is like calling, it is like trying to delete with sudo all the kernel files. You can do it, but you will ruin the system. But normally, if you do not have such privileges, you cannot kill it, even if you try to kill it, because it belongs to somebody else. It belongs to root. So what happens? Ya hocam, yani if these are diyebilirsiniz ki, you can ask, hocam, if these are short integers, that means there is only a limited number of process IDs. What happens when they end? What happens when we reach the maximum number? What is the maximum number for a short integer? Unsigned.
$256.
Kaç? Yeah. So here we have the man page for the process ID. What does it return? The process ID returns the process ID of the calling process. Get parent process ID returns the process ID of the parent of the calling process, and so on and so on. Errors, nodes. I don't get anything extra about it. No. So if we are talking about an unsigned shortint, of course it would be about 65,000 approximately. But of course that is still a finite number. So what happens if you try to create more processes than that? Well, if you run out of process IDs, what happens is that the process IDs, they wrap up when they are maxed. So if you reach the maximum number, it returns back to the beginning, but not to 1. It starts from a safe minimum number, such as 300, 400, or 500, and it tries to find process IDs that are available. So processes that have already ended, and so the process ID will be free. So it wraps up back to the beginning. Why not back to 1? Well, because at the first few hundred processes are the processes that belong to the kernel. That's why. Idojan, what happens when a process dies, so it terminates, then who is the parent of the children of that process? Let me repeat that. What happens when a process is terminates, then who becomes the parent of the children processes of that process that was terminated? When a process dies, when a process is terminated, all of its children are adopted by init. So init becomes the parent of orphan processes. Öksüz kalanları anında, yetim kalanları anında arkadaşlar init evlatlık olarak ediniyor. Otomatik. Dolayısıyla her daim bir sürecin parent process ID'si var. So this means that there is always a parent process ID for a process.
Hocam eğer öldürülmezse onun adı zombi proses oluyor değil mi?
We will get to that when we talk about processes in detail. Not exactly like that. We will talk about zombies in the upcoming weeks. Don't worry. Now, let's finish up with this stuff first. Now, this brings us to the topic of memory layout. Now, how is the memory organized in a process? What are the pieces? What are the segments? What are the regions of memory in a process? Now, they are termed segments, and of course, this is not the first time that you hear about them. I know that you did this stuff also during assembler programming. So we will try to get into more detail now from the point of view of system programming. Now, what are those segments? Well, of course, we have the text segment, which contains the code, the instructions of the program that we want to execute, that is supposed to be executing. And the text segment is, of course, read-only. It is made read-only by the kernel. So when the kernel takes those instructions, that executable information from the hard drive, it reads it from the executable file and places them into main memory, it automatically makes that section of the memory read-only. So no program, no running process can modify its code while it is executing. This is for protection purposes. This is how POSIX works. The text segment is read-only and nobody can modify it. Once the code is read from the hard drive to memory, that's it. That is the code. It also has, of course, the initialized data segment, which contains the initialized global and static variables. Of course, the uninitialized data segment, similarly for uninitialized global and static variables. Of course, the stack, which is growing and shrinking dynamically depending on how many function calls we make, which is there in order to contain, of course, local variables, function parameters, and of course, function addresses. And of course, we have the heap, which we use in order to allocate dynamically memory at runtime using malloc, realloc, calloc functions. Now, here we have an example, a standard C program. We have a global character globBuf. It is uninitialized, so it will be living in the uninitialized data segment. There is an array of integers. It is initialized explicitly, so it will be living in the initialized data segment. There is also, of course, we can see a static function. Now, of course, the function parameter will be in the stack, in the stack frame. It has a local variable also in the stack, and the return value of functions always it is passed through registers. Return values, they are always passed through registers. Similarly, here we have another function. Of course, its variable, its parameter will also take place in the stack. Its local variable t will also be in the stack. The main function, also of course in the stack frame with its command line arguments. It has a static variable that is initialized, so it will live in the initialized data segment. It has a dynamically allocated 1 kilobyte memory region. Of course, it will be allocated from the heap and so on. So you can see that in the same program, you can have multiple variables that reside, that live in different regions of the process memory. And here we have a better illustration. These illustrations are from the Advanced Linux Programming book that I talked to you about, which is included among the books of this course. I highly recommend that book. You can find it online very easily. It's freely available, no copyright. Now here we have a excellent illustration, and we can see that the virtual addresses, they are growing towards the top. So we start from 0 and they increase as we go to the top. These are virtual memory addresses. At the very top, we have the kernel, which is mapped into process virtual memory, but it is not accessible, of course, by the program. We have the argv and environ variables, which contain the command line arguments of the program, which contain the environmental variables that are given by the kernel to the process. We have, of course, the stack, which is growing downwards. And at the beginning, at the bottom, of course, we have the text, so the program code, which is read-only. We have the initialized data, global and static variables that have been initialized, BSS for the uninitialized data, and then we have the heap, which is the part where you allocate data by using malloc, realloc, and calloc. If, for instance, I execute the size command for ls, I can see from the executable file how much memory it is supposed to use if I execute it. So there are approximately 124 kilobytes of instructions, approximately 5 kilobytes of initialized data, BSS for the uninitialized, approximately also 5 kilobytes, and so on. So in total, in decimal, we have approximately 133 kilobytes required for ls. So you can use the size command in order to study in this way the executable files on your system before even executing them. Now, a common question is, Hocam, why do we have two different sections, two different segments for initialized and uninitialized data? And the answer is, of course, for optimization. Because otherwise, if everything was in the data segment, initialized and uninitialized, it will contain a lot of zeros, and it would require skipping RAM spots, and that reduces the efficiency of especially embedded programs. Now, we are not going to talk in detail about virtual memory management today, but I will give you a little more information with respect to what we talked about last week. It is Yusuf Hoca during the operating system course that will explain them all in detail. So what's the deal with virtual memory management? I mean, why aren't we using the memory directly? Why do we need a layer, an additional layer of virtual memory management? Bu sanal belleğe neden ihtiyaç var? Efendim?
Can I ask a question before start virtual memory management?
Well, we haven't even started explaining it, but yes, you can ask a question.
You said that instructions are stored in the describe a.out file.
I'm sorry, the instructions are stored what?
Disk, right before the execution. And
well,
then
yes. The executable file is on the hard drive, yes.
Then moving the start the execution, instructions are moving the main memory, right?
Yes, they move to main memory.
This is happening
right here in text.
Okay, this is happening when we do it. Write the terminal a.out, ./a.out right before that.
Mr. Mohammed, this happens when you execute a program. It doesn't matter how you execute it. You can execute it from the command line by clicking ls. You can execute it like this. You can execute it by double clicking. Where is it? Burada değil. Yukarı götür beni. Nasıl gideceğiz burada yukarı kerataya? Vay anasına. Bunlar şey yapıyordu. Uğraştırıyor insanı. İşte bu yüzden komut satırını seviyorum arkadaş. You can execute it by double clicking it. You can executing it by using a voice command. You can execute it any way you like, Mr. Muhammad.
Okay.
It will still lead to the same thing. It will
Also,
still the copying of the
macros.
contents of the executable file from the hard drive to memory.
Okay. So macros and preprocessors are also storing this aşama. Bu aşamada mı hocam main memory'e konuyorlar?
Muhammed Bey Türkçe sorunu soruyor.
Hocam preprosesörler var.
Mikro işlemciler evet.
Mikro işlemciler. Ve makrolar falan bu aşamada mı konuyor? Main memory'e konuyor.
Ha bak makrolara geldiniz siz şimdi. Şimdi bak makrolar ayrı bir konu. Makrolar sizi kodu yazarken vardılar. Siz derledikten sonra uygulamanızı o makrolar da zaten executable'ın binary'nin içerisinde zaten kod olarak, binary kod olarak duruyorlar. Komut olarak duruyorlar. Makro olmaktan çoktan çıktılar. O kısım derlemede oldu. Yani makroların koda dönüşmesi. Bir defa derleme bittikten sonra yani compiler işini bitirdikten sonra linking aşaması son aşama hatırlarsanız. Hatırlıyor musunuz derleme aşamalarını? Preprosesör çalışıyor, compiler aşaması var, linking aşaması var. Orada teker teker onları inceliyor. Önce yorumları ortadan kaldırıyor. Makrolar varsa makroların kodunu yerine koyuyor. İşte başka bir yerden çağırdığınız fonksiyonlar falan varsa onları dosyaya yerleştiriyor. Derlemesini yapıp onları binary koda dönüştürüyor. Başka yerlerden çağırdığınız fonksiyonlar varsa printf gibi onların kodunu veya bilgisini içeriye kaydediyor. Buyur abi diyor sana bir tane dosya, bütün kod içeride. Ve artık hard drive'da yaşıyor, diskte yaşıyor. Ve sen onu ister çift tıkladın, ister // ile çalıştırdın, ister doğrudan komut olarak hangi şekilde istersen çalıştır ama çalıştırdığın takdirde kernel devreye giriyor, işletim sistemi alıyor güzel o dosyanın tek başına sadece bir dosya sonuçta o ya. Buyur burada bak işte LS'inki burada. Bütün komutlar buradalar. Okuyor buradaki içerideki atıyorum işte sleep için 35.000 byte'ı. Ne varmış o sleep'in içerisinde? Size sleep diyelim. İçeride 27.000 küsür kod varmış. 1288 initialize data varmış. BSS 448 uninitialize varmış. Toplam diyor yaklaşık olarak tam olarak 29.315 diyor bana bellek lazım diyor. Byte olarak sleep'i belleğe atmak için. O 29.000 küsuratı bu şekilde organize ediyor. İlk başa kodu koyuyor text. Ardından initialized, uninitialized. Heap için hazırım diyor. Oradan itibaren heap'i kullanacağım. Şu boş gri alanda. Stack da diyor yukarıda. Komut satırı argümanlarımız en tepede arg ve ortam değişkenleri de environ onlar da en tepede duruyor adres olarak. Bu yapıyı diyor kullanacağım.
Tamam hocam teşekkür ederim.
Now class, why virtual memory management? Back to our question. Why don't processes use directly? Why don't processes use directly the physical memory? And instead there is an additional layer of virtuality. Neden ek olarak bir sanallık katmanı var arada? Ne güzel doğrudan RAM'e ulaşacaktık arkadaş ya. Güzel. Sen şurayı oku, ben burayı oku falan bu işi halledecektik.
Because memory is not enough for all the processes.
Well, not only that, that is the main reason. Kim söyledi onu?
I did, sir, Gökbey.
Okay, thank you, Mr. Gökbey. Now, that is one of the main reasons. Now, let's get into more detail. Our objective is to use memory efficiently. The objective is to use it efficiently. The objective is to make sure that whoever asks for memory can at least get a piece of it. Of course, at this point, you might say, yeah, hocam, I mean, this is not rocket science. I mean, if you have 100 processes that require in total 32 gigabytes of memory, but you only have 8, that doesn't work. It shouldn't work. But that is where we are wrong. Why? Because people have studied programs, people have studied running programs, so processes, and they saw two things. The locality of they saw the locality of reference, which translates to two kinds of locality. They saw one, spatial locality and temporal locality. What is spatial locality? It is the tendency of a program to reference memory addresses that are near those that were recently accessed. belli bir yerdeki bir adresi okuduysa ona yakın adresleri okumaya eğilimi oluyor uygulamaların. And not only that, there is also temporal locality. Processes have a tendency to access the same memory locations in the future as the ones that they accessed in the past. So this means that a running process will not necessarily need to access all of the variables in the process's memory space all the time. Eventually, it will access them. Eventually. Maybe at the beginning, maybe at the end, maybe once, maybe twice. But it will not need all of the memory at every moment. So this means at any given moment, you can only keep in memory a small part of the memory space of this process and still keep the process executing normally. Bu kısım net mi arkadaşlar? Tekrar açıklamamı istiyor musunuz? How do we exploit this? We exploit it by virtual memory management. Basically, here on the right, this is a very simple and accurate depiction. On the right, we have physical memory. It has been divided into frames. It can be divided into anything you want. Bytes, kilobytes, frames, pages, segments, anything you want. That's a matter of organization. So here, let's say that the memory has been divided into frames. And each frame is, I don't know, 1 kilobyte, 4 kilobytes, 8 kilobytes, whatever you want it to be. Now, the process, on the other hand, has access to this virtual address space. And this virtual address space is also made up of page frames. It's made of pages. And each page, as I said, each page frame can be 4 kilobytes, 8 kilobytes, whatever we want it to be. So the trick is that even though the process sees a continuous flow of addresses starting from 0 all the way to the 8th gigabyte in your system, it thinks that all of the bytes are available to it, but in reality, it has only access to some pages. For instance, here, it has only access to 5 pages from 0 to 4, but these do not correspond to the actual 0th page on the system in the physical memory. The system goes through the kernel. That's what I mean by saying system. Whenever the process tries to access, for example, page number 2 in its virtual address space, the kernel looks into the page table of this process. It sees that page 2 corresponds, in fact, to number 7 in actual physical memory, and it goes to the 7th page in physical memory in order to read the contents of page 2 in the process's virtual address space. Why did we do this? Why did we add this additional layer of complexity? So that we can benefit from the spatial and temporal locality, so that we can benefit from the fact that processes only use a subset in order to benefit from the fact that processes only need a subset of the memory space at any given moment. And thanks to this, we get to what Mr. Gökbey said. Thanks to this, we are able to run way more processes that in total require way more memory than the actual memory that is available. So right now in my system, for example, we are at process ID 5000. So I am writing at least 1,000 processes at the moment, which maybe in total require, who knows, 64 gigabytes of memory. But I only have 16 on this system, thanks to virtual memory management. And what happens, of course, when a process tries to access a page that doesn't own yet? Well, segmentation fault. Or in system programming terminology, it receives the signal, which corresponds to a segmentation fault. So this is very easy. It becomes very easy for the kernel to check whether a process is actually accessing a memory space that belongs to it or doesn't. All it has to do is, when you access a memory location, is to check the page table. If that address exists in this page table, then it is your own. If it doesn't exist, segmentation fault. Now, what about the stack and stack frames? Now you know about the stack. Of course, the stack is used in order to contain local variables, function addresses, and of course, function parameters. And of course, we have the stack pointer, which is a special purpose, of course, register in the CPU. And of course, it keeps track of where the top of the stack is. And every time that we call a function, the stack pointer is updated and the stack grows larger in order to contain the local variables, in order to contain the function return addresses, in order to contain the function variables. Now, there are two kinds of stacks. There is a user stack and there is a kernel stack. And not only just one kernel stack. There is one user stack for every process, and there is also one kernel stack for every process. Why does the kernel keep a process-specific kernel stack? It is keeping it in order to keep track the system calls that this process has requested to execute. So when it executes a system call, which is also, of course, a function, of course, it needs to use a stack. Which stack is it going to use? If it uses its own stack, because the kernel also, of course, will have its own specific to the kernel stack. If it uses that stack for all the system calls of all the processes, everything will be confused. Instead, it keeps a separate kernel stack for the system calls in every processes for every process independently. So in total, how many stacks do we have? A lot. We have one user stack for every process. We have one kernel stack for every process. And of course, we have the kernel, we have the stack that belongs to the kernel itself. I mean, the kernel itself is also a process in the end line. So that makes a lot of stacks. Now, class, I am assuming that you have already used command line arguments in the past. Is that right? In C programs, argc and argv?
Yes.
Okay, as I guessed. So as you already know, argc contains the number of command line arguments, and argv is simply a null terminated array which contains, again, null terminated character arrays of the command line arguments. And of course, they are available to every C program as long as you declare them as parameters in the main function. So this is not new for you. You can easily access these arrays in order to get hold of the command line arguments. So I'm passing through them. However, what you haven't used so far is the environmental list. Now, the environment list, or simply the environment, is just a collection of strings. It is simply a collection of strings which are of the form name equals value. Now, these are variables and values along those variables that are provided to each process by the kernel. Now, what kind of information is provided? Now, we can, for example, type env in order to access the environment. So here we can see, for instance, the important ones. Home, of course, the home folder or the current user, pwd, the present working directory, the user, the username, the path, so where to look for binary files. All of these are available to all of the processes that get to be executed. So how do you access these? Are they read-only? No, they are not read-only. You can modify them. You can declare new environment variables. So here, for instance, we can see a small program that accesses the environment list by simply including the external variable, which is simply a list of strings, a string of strings in a way. And of course, you can manipulate them. For instance, it is using puts in order to print on screen all of the environmental variables, just like I did previously. You can additionally use these library functions, getenv, in order to read a specific variable, for instance, user, pwd, path, home, and so on. You can use putenv and setenv to create new variables, to modify their values, in order to delete them, and so on. So the environment list is completely at our disposal. So you do not have to wonder when a process works, what is my home folder? You can simply read the environment list and figure out the home directory. That brings us to memory allocation now. how do you allocate memory on the heap? Now, you already know from the past that you can use malloc, realloc, calloc in order to allocate memory from the heap. Now, what you don't know probably is this part. Now, just like the top of the stack is kept by the stack pointer, the top of the heap is also kept stored as a variable known as program break. Program break, the end of the heap. So when you use malloc, realloc, calloc, or whatever in order to allocate additional memory, all it does, it modifies the location of the program break. Just like when you create new local variables, you simply modify the stack pointer. When you allocate new memory with malloc or calloc, you just move the program break so that the heap will become larger. Now, the malloc family of functions are not system calls. They are standard C library functions. Now, behind the scenes, malloc, realloc, calloc are using bereke, sbereke, break, and sbreak, which are used in order to modify the program break. So behind the scenes, behind malloc, realloc, calloc, we have these two system calls. Bereke, which simply returns 0 on success or -1 on error. And what do? It is simply used in order to modify the program break in order to include, let me use proper terminology, man bereke. So what does bereke and sbereke do? They change the location of the program break, which defines, of course, the end of processes data segment. Bereke, it sets the end of the data segment. So whatever you give it as address, that will be the new program break. And what does sbereke do? Sbereke, it increments the program's data space by this number of bytes. So you give it, for instance, 100, the heap will grow larger by 100. You give it 10 megabytes, the heap will grow by 10 megabytes. Whereas bereke, it receives directly the address, directly the new location of the program break. Of course, we do not use them. We do not use these system calls dynamically. Instead, all of us, we use malloc, realloc, and calloc because they are much more user-friendly and they help us to avoid errors. They are standardized parts of the C language. They are easier to use in threaded programs, and it's a simpler interface. Now, additionally, of course, we have the free function. Now, if malloc makes the heap grow larger, does free make it grow smaller? Not exactly. Not exactly. Now, here we have malloc. We will get to free in a moment. Now, here we have malloc, which, as you already know, it receives a certain number of bytes to allocate. If it is successful, it will allocate that portion of memory from the heap by modifying the location of the program break, and it will return you the address to the first byte of the amount of memory that has been allocated. You should always check whether it returns null or not. Now, about free. Now, free, of course, as you know, it lets the kernel know that this pointer and the memory region that this pointer is pointing to is no longer necessary. Now, does this mean that it is returned to the system? Does this mean that the program break is lowered? No. In general, not always, in general, free does not lower the program break. Instead, it just lets the kernel know that this portion of memory is now available. So if somebody calls malloc again, the kernel will be able to allocate that region that has been freed to the process once again. So it is basically recycling memory locations. When a process terminates, all of the memory that it was allocated to it returns to the system. When a process terminates, for whatever reason, it dies, it is killed, it has an accident, who knows? Maybe it commits suicide. When the process dies, all of the memory that it allocated, stack, heap, BSS, uninitialized, initialized, text, all of the segments are returned to the kernel, are returned to the system. regardless of whether you freed them or you didn't free them. That's how POSIX works. Now, because of this, some developers, students mostly, they choose not to free the amount of memory that they have allocated. This is very bad practice, and it usually leads to memory leaks when a process runs for a long time. So it keeps on allocating memory occasionally if it runs for a long time, but if it doesn't free anything, eventually it grows too large. So always make sure that you free whatever memory you no longer require on your system, on your process. And when the program is about to end, make sure that you free everything explicitly before the process terminates. Even if you forget it, when the process terminates, all of it will be returned to the kernel down to the last byte, regardless of whether you free it or not. But it is generally good practice to free everything, even before you terminate. Hocam, are there any other methods of allocating heap memory? Well, of course, there is calloc, which is very similar to malloc, but instead of receiving a number of bytes, it receives a number of units, so 10 shorts, 100 doubles, 5,000 floats, and it allocates them in that way. An important difference between malloc and calloc is that calloc initializes the allocated memory to 0, whereas malloc does not allocate it. So calloc is a bit more expensive in computationally speaking. There is, of course, also realloc, which is used in order to modify the size of a memory portion that has been allocated. So you can give it the address of the memory region that you want to resize, and of course you can give it the new size. And if it is successful, it will resize it. But pay attention that the new pointer that it returns might be different. So it will not necessarily return the same address that you gave it originally, if it is successful. And finally, something that you definitely haven't used before is alloca. Now, this is a very lesser known function, also available in the malloc package. So it is also a library function, not a system call. What it does is it allocates dynamically memory, but not from the heap, but from the stack. So you can use it, for instance, to allocate 1 megabyte from the stack dynamically. Hocam niye böyle bir şey var? Why does this exist? I mean, we can allocate from the heap. We can declare local variables which also exist in the stack. Why do we additionally have a function, a library function, to allocate memory from the stack? It is fast. It is extremely fast. You just simply give it the number of bytes that you want to allocate. They are allocated. And when the function that called alloca terminates, it is automatically returned to the system. So that means you should never call free on memory region allocated by alloca. The problem with alloca is that it is not very portable. The advantage of alloca is that it is way faster than malloc, way faster than malloc. But since it is not supported by ANSYS, as I said, it is not very portable. It is definitely not POSIX compatible. So if you are conscious about portability, if you have portability issues, avoid using alloca, just like you haven't used it until today. But if for some reason you are in an embedded environment, you are in a real-time environment, and you need to allocate a lot of memory very, very fast, then alloca might be a good solution. Arkadaşlar benim bugünlük anlatacaklarım bu kadar. Do you have any questions? Anything at all?
Everything was perfectly clear, sir.
Okay, thank you, Mr. Mohamed. From anyone else? We have time. Okay, class. Let's get to the real questions. Hocam, bu hafta ödev olacak mı? Is there a homework this week? I don't know. We'll see. If there is a homework, you will see it on Teams. Mr. Aygun says, can we make system calls on a virtual machine Ubuntu Linux? Of course. Of course you can make it. I mean, even if it is on a virtual machine, I mean, you can still execute system calls. It is an OS. It is working virtually, but I mean, the host operating system, it is doing what? The host OS, the host operating system, is making the virtual machine think that it is actually native install. So all of the system calls, they in fact work perfectly well. But of course, they have to go through the original operating system. But still, they will work. All of them will work. There is just a translation layer between the virtual machine and the original host. Yes?
How come the original operating system can understand the system call if it doesn't have that system call?
If it doesn't have it, well, basically what it does is it allows for the client, not the host. It allows for the client operating system to execute natively. It gives it that privilege. That's why whenever you execute the virtual machine, you need to do it with administrator privileges, with root privileges. And besides, that is also the reason why I asked all of you not to make virtual machine installations, but native installations, because things can go wrong. Even though the virtual machine software guarantees that things will be just like a native install, sometimes they are not. And we will just lose a lot of valuable time trying to debug those errors. So that is why please make sure, if you haven't already, to have made native Linux installations on your machines, please. Those are usually a great source of errors.
Thank you.
Okay, thank you, class, for your attendance. Next week we will have even more interesting stuff to continue with. Bu hafta ödev olsun olmasın. I will think about that. Okay, thank you, class. If you have any questions, send me emails. I will try to answer them to the best of my ability, and I will see you next week on Wednesday. Take care. You too, class. Bye.